Welcome to Module 8 on work energy method for rigid bodies under planar motion. This module is analogous to module number 4, which was concerned with work energy method for particles. So in that particular module, we were idealizing physical objects as particles where all their mass was concentrated. And in this particular module now, we are going to be idealizing our physical objects as rigid bodies that would be moving in a plane. So you will recall that for a particle that moved under the influence of a force, let's say the force is F and the displacement is dr, that's a differential displacement, then the total work done was defined as integral dw, which is integral F dot dr, and this was in general line integral. But for certain kinds of forces which we classified as conservative forces like gravity, elastic forces, universal gravitational attraction, the work done by those conservative forces did not depend on the path. We also could relate the work done on a particle with change in kinetic energy. So if we had a particle, then its kinetic energy was defined as half mv squared, and the change is always final kinetic energy minus initial. So we have 1/2 mv squared minus 1/2 mv initial squared, and this formula was always valid. We also saw that we could divide the work done by certain kinds of forces as work done by conservative forces plus work done by non-conservative forces. So frictional forces are almost always non-conservative. At the same time, you may have some unknown forces given to you in the problem which can also be non-conservative. In fact, any force whose nature is not completely known to you can be seen as a non-conservative force, like reaction forces and things like that. We also saw that the work done by conservative forces could be written as minus delta U, where U is defined as a potential energy function. And the potential energy function depended on the nature of the force. So you have one kind of potential energy function for gravity. So for gravity, we saw that U sub G was defined as mg times y, where y was the vertical distance above from datum. So the particle was here, then maybe this was the plus y1 and the particle moved from here to here, then the vertical distance was plus y2, and below the datum the distance is always treated to be negative. Similarly, the potential energy function for elastic forces, linear elastic forces, was defined as 1/2 kx squared, where x is deflection, it could be stretch or it could be compression, and you can see that this quantity is always going to be positive whether x is positive or negative because you have an x squared term. So these were some of the basic things that we learned in that particular module when we talk about work energy approach for particles. So we had a test over there which said that you use work energy method when you're trying to relate the forces, displacement, and the speed. Okay, so you can see that there was no consideration for acceleration, and if the acceleration was not as far, then the chances were that you could apply a much simpler work energy approach to solve the problems. It was simpler because this particular equation over here is actually a scalar equation. On the other hand, Newton's second law, which can be always applied to solve the problem, give rise to vector equations. Now the question is, what if anything changes about these relationships for a rigid body moving in a plane? So the definition of the work done by a force actually does not change. So this definition continues to apply. This relationship over here, that the work done is equal to change in kinetic energy, also does not change. And the work done can be divided into conservative and non-conservative forces also doesn't change. And work done by conservative forces is equal to minus delta U is also valid for rigid bodies moving in a plane. What changes for rigid bodies moving in a plane is the expression for kinetic energy. So the expression for kinetic energy for a particle is given as 1/2 mv squared, and this is for a particle. On the other hand, the expression for the kinetic energy for rigid bodies is slightly different from this. So let's first try to derive that. You will recall that the kinetic energy for a system of particle was given as sigma 1/2 mi vi squared, where mi is the mass of particle I and vi is the speed of particle I, right? So we can proceed along a similar line and try to derive the expression for kinetic energy for a rigid body moving in a plane. So rigid body, let's say we have a rigid body over here, and there is a differential mass of quantity of magnitude dm, and we have a center of mass. Let's say this is located at a position vector rho, and of course we have our reference frame. We have the position vector for this particle, for this particular differential mass, not particle, and that is, let's say, r sub g. And the point G, which is the center of mass, is moving with some velocity vg, okay, and the velocity of this differential mass is, let's say, v, okay. So kinetic energy of just this particular differential mass is given by the mass times this speed squared, right? So integral dmv square would give you the total kinetic energy of the rigid body. So you take dmv square and you integrate it over the whole rigid body, and you get the total kinetic energy. And this is, very similar to this expression over here, where instead of integral we have sigma, and of course we have to add 1/2 in the front, right? So that's the only thing that we have over here. Now the velocity of this particular differential mass can be written as velocity of g plus the angular velocity, let's say this is the angular velocity, cross the position vector of the differential mass with respect to center of mass. And this is coming from module number 6 on kinematics of rigid bodies moving in a plane. So what is v square? V square can be written as v dot v. So if you take the dot product of velocity vector v with itself, you get the magnitude of velocity squared. So let's substitute for vg plus omega cross rho dotted with itself and see what we get. So vg dot vg is clearly vg square. Then we have plus vg dot omega cross rho plus omega cross rho dot vg. So that's a dot b is equal to b dot a. So this will be basically 2 plus omega cross rho dot omega cross rho. Okay, so that's what we have for the v squared. Now let's try to simplify this whole thing and see what we get. So omega cross rho, what is omega cross rho? Omega cross rho is omega k hat cross, let's say rho is rho x I hat plus rho y j hat. Since we're using a translating frame, so we can use, these unit vectors, okay, right? And that's the frame attached at g as well. So this is equal to omega times rho x k cross I is j plus rho y k cross j is minus I. So that would be, let me erase this. Let's say this is actually minus I hat, okay. And omega cross rho dot omega cross rho, which is this quantity, would be equal to, so omega cross rho dot omega cross rho would be equal to omega times rho x squared plus rho y squared, right? So we get that, actually it's omega squared, not omega, so we have the square of that. Okay, so let's substitute for these two relationships over here, this and this, in our expression for v squared. So we get v squared equal to vg squared plus 2, we have vg dot omega cross rho, so vg dot omega rho x j hat minus rho y I hat plus omega square rho x squared plus rho y squared, okay. So this can be written as vg square plus 2. Now vg is a velocity vector in a plane, so that can be written as some vg x I hat plus some vg y j hat dot omega rho x j hat minus rho y I hat plus omega square this. Now keep in mind that all this analysis that we are doing, starting from this point onward, when we introduce a simplification, is going to be for a rigid body moving in a plane, okay? If this was not moving in a plane, that means angular velocity would not be in a direction perpendicular to the xy plane, then we won't be able to introduce these simplifications. Okay, so let's take the dot product of the second term in here, and we get 2 times. So I dot j is of course 0, so this would be minus vgx rho y plus rho x vgy, and we have omega plus omega square rho x square plus rho y square, okay. Now we can substitute for this v squared in our formula for the kinetic energy of a rigid body. So let's do that. So we get T equal to 1/2 integral dm, and v squared is vg squared plus, let me use square brackets over here, plus 2 times minus vgx rho y plus rho x vgy omega plus omega square. Okay, all right, so now I'm going to take the dm inside each of these three terms, and we'll get 1/2 integral dm vg squared plus 1/2 integral, so this is 2 here, dm times minus vgx rho y plus rho x vgy omega plus 1/2 integral dm times omega square rho x squared plus rho y squared. Okay, so vgx is clearly, a velocity in the x direction, so that's something we can take outside of this integral. This 2 cancel, so you get 1/2 vg squared here comes outside. This is integral dm. Okay, so that will be just the total mass. All right, so this would reduce to the total mass. This is minus vgx integral rho y dm plus vgy integral rho x dm, and we have omega here as well, so let me write that, plus 1/2 omega squared comes outside, we get integral rho x squared plus rho y squared dm. Okay, so now let's look at what these terms are. So we have 1/2 the total mass of the rigid body, vg squared, and I'm going to write this term first now. So this is integral dm rho x squared plus rho y squared. Rho x squared plus rho y squared is actually the square of the distance from the center of mass to the differential element, right, which is this distance right over here, and that actually gives you the distribution of the mass about center of mass. And you know that this quantity is actually called centroidal mass moment of inertia, so that's plus 1/2 ig times omega squared. Now let's look at this term. What is integral dm rho y? Integral dm rho y is basically giving you the y component of the center of mass with respect to center of mass, because rho y is the distance of the differential element from the center of mass, which means that this quantity has to be necessarily 0. And using the same logic, this quantity also has to be 0. So the T for the rigid body is basically composed of 2 terms only, 1/2 mvg squared plus 1/2 ig omega squared. Now this is an interesting expression, because you can see some part of the kinetic energy expression for a particle in here, which is 1/2 mvg squared, which is to say that if you took your rigid body and treated it as a particle, then particle by definition wouldn't have any angular velocity, and that means that this term would drop out. So you would be reduced to the same expression that you have for kinetic energy of a particle. So this is the general formula for a rigid body moving in a plane. Now, in this expression, these 2 terms have a specific name. This is called translational kinetic energy, while this term is called rotational kinetic energy, because the rotational kinetic energy term arises from the rotation of the rigid body, and if it is a non-zero omega, then rotational kinetic energy would be non-zero. Translation kinetic energy arises from the fact that the center of mass of the rigid body has a finite linear velocity, and if that finite linear velocity was 0, then translation kinetic energy term would drop out. But in general, if you have both translation of the center of mass as well as the rotation of the rigid body, then those 2 terms would add together. So let me give you a simple example. Let's say I have a wheel rolling without slip, and the center of mass has the velocity v0. So rolling without slip says that the contact point momentarily has 0 velocity. That means this is also the point of instantaneous center of 0 rotation, and that means that v0 is equal to the radius of the wheel times its angular velocity. Okay, so angular velocity can be written as simply v0 over r. Now remember, this is valid only when no slip condition is introduced. So no slip. Okay, if it was slipping, then the angular velocity could be entirely different from v0. Maybe the rigid body was moving, but it was slipping at the same time, which is what happens when you sometimes throw a bowling ball. In the beginning, the ball rolls while it is slipping as well, and at that time, there is no correlation between the velocity of the center of mass and angular velocity. So knowing this, now we can write the kinetic energy of the wheel as 1/2 mvg squared plus 1/2 ig omega squared. Vg is given as v0 plus 1/2 ig omega is obtained as v0 over r squared. Okay, what is ig? Ig is the centroidal mass moment of inertia. So if you model this wheel as a cylinder, then that's given as m times r whole squared over 2. Okay, if it was treated as a sphere, then ig would be 2 or 5 mr squared. If it was treated as a ring, it would be simply mr squared. So depending on what kind of shape you have, you'll have a different expression for kinetic energy, because ig would be different. Now on the other hand, if you took this wheel and you constrained it to just rotate about its center of mass like this, and this was only allowed to rotate, in this case Vg, velocity of the center of mass, is 0 because it's a fixed point, but it still has kinetic energy, because in the expression for kinetic energy for a rigid body moving in a plane, this would be 0, but you would still have the rotational kinetic energies, because in this case the rigid body is doing a rotation about center of mass, and that would be equal to 1/2 mr squared over 2. This is assuming it's actually a cylinder, times omega squared, right? So whenever you use kinetic energy formula for a rigid body moving in a plane, always remember to use this formula. Don't just write 1/2 mv squared unless you know that rigid body is only doing translation and has no angular velocity whatsoever. Now, for certain cases when there is rotation about a fixed point, and remember this fixed point does not have to be necessarily a center of mass. So if I take a rigid body and I fix this rotation about a point, let's say O, we can achieve some simplification in the expression for kinetic energy. So let's say center of mass is here. So clearly if this is rotating with angular velocity omega, then we can find out what this would be. So Vg would be equal to the distance from O to G, let's call it rho, would be rho times omega. Okay, so we don't care about the vector quantity over here because we're just dealing with scalar quantities. Then kinetic energy for this rigid body is 1/2 mvg squared plus 1/2 ig omega squared. Vg, because this is rotating about a fixed point O, is rho omega whole squared plus 1/2 ig omega squared. So this is 1/2 ig plus m rho squared. I'm writing this term first, times omega squared. Now what is this quantity over here? This is centroidal mass moment of inertia plus the mass of the rigid body times this distance squared, which is the perpendicular distance between the two axes going through point O and center of mass. From parallel axis theorem, you know that this is equal to I sub O times omega squared. So when a rigid body is rotating about a fixed point, it turns out that the kinetic energy formula can be written simply as 1/2 the mass moment of inertia about the fixed point of rotation times omega squared. So in this case, you're not going to add kinetic energy term due to translation because you already took care of that. In fact, you obtained this because you added these two terms and Vg was substituted as rho omega. So let me give you a simple example. Let's say we have a platform of given mass, and this platform is connected via two rods like this. Okay, so let's assume that only the platform has some mass. The rods have no mass whatsoever. Then the question is, what is the kinetic energy of this rod, this platform, as it rotates about this fixed point O? So this is a fixed point rotation, so kinetic energy can be written as 1/2 I sub O, which is the centroidal mass moment of inertia about the point O of the rod, times omega squared, right? So how would you compute what IO is? Well, IO is equal to the centroidal mass moment of inertia of the platform, which let's say is, the point is G, so that's IG, plus the mass times the perpendicular distance from O to G. So let's say this distance is h, then this would be m times h squared. And that would be the kinetic energy for this platform as it rotates about fixed point O. You can also use instantaneous center of zero velocity to write the kinetic energy for a rigid body. So this is another example. So let's say I have a slider, and here is another slider. So this is actually a double slider mechanism. And this is coming down, let's say with velocity VA, and that's point A, okay? And this point is called B, so this is going that way with velocity B. Right here is the center of mass, and the mass is given, the length of the rod is given. Assume that the slide is massless. And we're looking for the kinetic energy of the rod at this particular instant, okay? So we're looking for it, kinetic energy at this particular instant only, because at different instant, the kinetic energy may be different. So we can, of course, write the general expression, which says 1/2 mvg squared plus 1/2 ig omega squared, but you can locate the instantaneous center of zero velocity, about which point this rigid body, this rod is momentarily rotating, and treat that instantaneous center as a fixed point. So first thing is we have to locate where that instantaneous center is. So you will recall from the discussion in module 6, kinematics of rigid bodies and moving in a plane, we have to locate the velocity vector directions of at least 2 points on the same rigid body and then draw perpendiculars to those velocity vectors. So point B has velocity vector that way, point A has that way, so we draw the perpendiculars to those velocity vector going through the point A and B, and this is where at this instant instantaneous center is located. So now we can say VA is equal to this distance. So if this angle is theta, then this angle is theta, and that means VA is equal to L cosine theta, which is this distance. This is L cosine theta and this is L sine theta times omega. Okay, so if VA is known, then omega can be directly obtained from that. So omega would be equal to VA over L cosine theta. At the same time, you can write velocity of B is equal to L sine theta times omega. So instead of VA, if VB is given, then omega can be written as VB over L sine theta, right? Kinetic energy of a rigid body rotating about a fixed point, in this case is instantaneous center, would be equal to 1/2 I times, let's call this point O, times omega squared, right? So all we have to do is now write down what IO would be. So using parallel axis theorem, IO is equal to IG plus m times the perpendicular distance between O and G. So if you draw this and you find what this perpendicular distance is between O to G, between what that distance is, then m times, let's say this is rho squared, would give you the IG, right? And that's how you can solve problems much more simply if you use the instantaneous center method to get the velocities. And that's one of the major advantages of using instantaneous center, because you can get some of these velocities and angular velocities very, very quickly, as opposed to using full-fledged vector equations, which you can still use, but it'll take you slightly more time to solve the problem unless you use instantaneous center method.